So today we're actually going to start an interesting new topic, which is pipelining. And so we're basically going to start to learn how can we take these designs that we've produced and improve them from a performance perspective. So let's think first of all about what are the performance measures that we care about. So there's two metrics that we care about in particular. The first is what we call latency. So latency basically measures the amount of time from when an input arrives at your circuit to when the output corresponding to that input is produced. Okay? And that's certainly, an important measurement. But the other one that we care about is throughput, which is the rate at which inputs or outputs are processed. So depending on your application, you might care about a different metric, and so you might optimize differently depending on what it is that you're optimizing for. So for example, suppose that you're trying to build an airbag deployment system. Which of these two metrics do you think you might care about more? Latency or throughput? I think I heard latency, right? I don't really care how many times I can get the airbag to open in a second. I want it to open as quickly as possible when I actually need it, right? On the other hand, if I'm talking about a general purpose processor, then I might be willing to give a little bit in terms of how long a particular instruction takes if, on average, my instructions are going to be able to run faster. So here, what I'm trying to maximize is the throughput, which is the maximum instructions per second, rather than just worrying about the shortest delay for every single instruction. All right, so let's start with some combinational logic and get a feeling for these metrics and how we would go about measuring them for different circuits. So here what we've got is a combinational circuit with three modules in it, F, G, and H. And the latency of any combinational circuit is basically always the propagation delay, which is the delay of the longest path of our combinational circuit. And throughput is defined as 1 over that propagation delay. So this might, make you think about, well, are we really, using our hardware in the best way possible? So, regardless of what's going on in the circuit, I can't get my output any faster, right? I have to first go through F and G, and only when those two computations are done can I go ahead and have H run, right? So if I look at a little bit of a timing diagram of what's going on in the circuit, it looks something like this. So here's my input X ready to go into my circuit. And after some propagation delay, F is finished processing that X and has produced a valid output. G takes a little bit longer, but at this point, it's produced a valid output. Now, only at this point can H go ahead and get started. And so H starts computing over here, and it's got this space of time for the propagation delay. But if you look a little more closely at this, you notice that F and G are actually not doing anything useful while H is doing its computation. So that's kind of wasteful, right? So what we'd like to do is figure out a mechanism to avoid that. And the way that we do this is we basically add registers into our combinational circuit like this. And this is what we mean when we say we pipeline a circuit. So let's try to understand what happens here. So what we've done is we've added a register at the output of H, and we've also added a register at the output of each of the F and G modules, okay? And here let's consider, a particular example where we've been giving latencies for each of these modules, and so it's the number inside the box corresponds to the latency of that module. And so let's go ahead and analyze, how this circuit compares if we run it as a combinational circuit versus a pipeline circuit. All right? So first thing we're going to take a look at is the combinational situation. So how did I get a latency of 45 for the combinational circuit? Yep. Yeah, so it's the longest propagation delay, which is through G and H, okay? So my longest propagation delay is 45, so that defines my latency. And and my throughput is 1 over that latency. Okay? Now, let's talk about this two-stage pipeline. Okay? And the reason that we call it two-stage is because you can think of in stage 1, F and G are computing, and then their outputs go to H, and while H is computing, F and G can start computing on the next input. Okay? So, what would the latency of this pipeline circuit be? What do we think? What's going to determine how fast I can clock this circuit? Yeah?
H being the longest to propagate?
H, exactly, is the longest to propagate. And so, in general, I really need to worry about every register-to-register path. And so, if I also had, non-ideal registers, these ideal registers tell me that the propagation delay and the setup time of the registers are 0, so I can ignore them. If they weren't 0, I would have to add them into my calculation and figure out the longest register-to-register path. But so here, that longest path is 25, which means that my clock period has to at least have 25 time units in it in order for H to be able to do its job. And now, in order to actually have input X make it all the way to P of X, I need to go through 2 of these cycles. And so my latency is going to be 2 times 25, or 50. But what's my throughput in this circuit? How often am I producing outputs? Yep.
Every 25?
Every 25, exactly. So even though my latency has gone up a little bit versus the combinational circuit, my throughput is now much better because now I'm able to produce an output every 25 time units, or let's call it nanoseconds. Okay? And so this is much better. All right? Any questions about this so far? Yeah.
Wait, where did you get the 2 times 25 from?
So basically what happens is we have to run 2 iterations of the clock, is what you can think of. And so in the first iteration, I'm having F and G do their computation. But even though F and G are faster than 25, my clock has to run at a set speed for every single cycle. So in that first cycle, it'll still take, let's say, 25 nanoseconds. And then after those 25 nanoseconds, I go to my second cycle, and that's another 25 nanoseconds. And so the output associated with input X isn't available until 2 cycles later. So 2 times that clock period. Okay? Any other questions? All right, sure. So it actually helps to think about pipeline circuits by using what we call these pipeline diagrams in order to figure out exactly what's going on in which stage of our pipeline at any point in time. Because clearly we're as we're getting into larger pipelines, we're going to be running multiple portions of different computations at the same time. So what does a pipeline diagram look like? Well, basically what we've got is our rows are our pipeline stages. And so here in stage 1, we have F and G running. In stage 2, we have H running. And then our columns are our clock cycles, or our time. And so basically at time I, we have our first input available to us. And so just before that clock cycle begins, X sub I has to be stable. And now during cycle I, F and G are going to be computing the outputs based on X sub I, or X sub, that is what is in here. Okay, so once that cycle completes, then the outputs of F and G can proceed into H. And so basically, we're going to be working on input X sub I at cycle I plus 1. It's going to enter the H module. And then at the end of that cycle, the output associated with this input is ready, right? So for a particular input, it takes us 2 cycles to go through the system because it's a 2-stage pipeline. And but at the same time that we're completing the computation for X sub I, in I plus 1, we can actually start the next computation, okay? And so basically, it ends up looking like this. Our data is going through our pipeline diagonally, and you're going to see that basically every single iteration, I'm producing another output. And so that's showing me that my throughput is 1 over 25, okay? And so this is a really useful tool, especially as our pipelines get more complicated. All right, so let's go ahead and have some definitions and conventions of how we deal with pipelines. So the first is what is exactly a well-formed K-stage pipeline? So we just took a look at a 2-stage pipeline. Of course, we can, for larger circuits, divide it up into more than 2 stages. And so in order to have a well-formed pipeline, you must have a circuit that's acyclic, and you have to have exactly K registers on every single input to output path, okay? And so we'll see what exactly that means in a second. And the other thing is that just by convention, we're going to say that every single output always has a register on it. And so the reason that we do this is because we want to have the ability to compose one pipeline circuit with another pipeline circuit. So essentially, if I have my first pipeline circuit, I know that it's got a register on the output of it, then I can add a different pipeline circuit after it, and it's got, a register at the end. And so I don't add to the clock period of any register-to-register path here because it's already covering the same time that I was covering in the clock period of the individual component, okay? So, and as far as the clock speed is concerned, we have to measure every single, in a pipeline circuit, every single register-to-register path, and the clock has to be long enough to allow for the longest propagation delay plus the setup time of the downstream register. So basically, to summarize, it looks like this. So for a K pipeline, we're going to have a latency of K times the clock period, and the throughput is 1 over that clock period. All right? So let's continue with this, and let's take a look at this example here and try to decide whether this is a valid pipeline or not. So what do we think? Probably from the title you can tell that it's not, but can anyone tell me what's wrong with it? Well, let's start taking a look. So if I look at every single input to output path and I count the number of registers on it, I see that in this first path, I have 2 registers from X going through A and C. In this path, with Y going through B and C, I also have 2 registers. But what happens if X goes through A, B, and C? Here I only have 1 register, okay? So what's the implication of that, okay? What is it going to do if I try to pipeline my circuit like this? What's going to happen is that you're going to end up mixing inputs that don't have to do with each other. So basically, when Y sub I comes to the input of B, X is already going to be on input I plus 1, okay? And so you're going to be mixing up your computations and not producing the right thing. So in order to ensure that your pipeline circuit works, you need to make sure that you have exactly the same number of registers on every single input to output path. So how can we do that in a kind of mechanical way that we can be sure will always work? We have a methodology for this. And so suppose I give you any kind of combinational circuit. What you're going to do is follow the following recipe. So the first thing you're going to do is you're going to draw a line that crosses every output in the circuit, and you're going to mark its endpoints as terminal points, okay? And so this is the first line that I draw. And wherever this line crosses one of my wires, basically I'm going to be adding a pipeline register, okay? So the next thing that I do is that I'm going to continue to draw these lines that are going to connect these 2 points. And I have to make sure that for every single line that I draw, that it's always crossing these arrows in the same direction. So in other words, you see here that we've labeled one side of this inputs and one side of it outputs, because notice that all of my values, all the data flow in this particular circuit are going from left to right, okay? So if I add another cross-section through this circuit, I've now separated out this last module, which is a 5 nanosecond module. And this is a valid pipeline because every single one of these arrows crosses from input to output, and so they're all going in the same direction, okay? So what is the implication of that? The implication of that is that if I now go back to my input and count the number of registers from every input to output path, the number of registers is going to be equal to the number of these contours that I've drawn, okay? Because each of these contours will result in a register wherever it intersects with my circuit. Okay, and so then I might, continue to draw some additional contours. And so now let's take a look at the details of this particular example. So what have I done so far? Based on, what I've drawn here, what would you say the clock period for this particular circuit could be? How fast can I clock this circuit? What's my limiting factor in this circuit? Yep.
Is it 8 nanoseconds?
It's 8 nanoseconds, exactly. So my slowest component is C, which takes 8 nanoseconds. So I can only put registers, before and after C. I can't, at least for now, put them inside C. And so basically, it must be the case that even if I have ideal registers, the amount of time that my clock period has to allow for is at least that longest module's delay, which is 8 nanoseconds, okay? So, what about, A and B here? Is there a need for me to separate A and B with adding another contour? Would it help me in any way? I see some shaking of heads, and that's correct. So there's no value in adding another contour between A and B because the sum of the delays of A and B are 4 plus 3, which is 7, which is still less than the clock period of 8 that we're going to have to set our pipeline circuit to, okay? And so basically, at this point, I'm done, and I've added these circles correspond to registers every single place where the contours cross my wires. And now if you look closely, you'll see that from every input to output path, I have exactly 3 registers. Okay, so I have a well-formed pipeline. And now let's think about how does this pipeline behave? Well, we said that the clock period is 8 nanoseconds, which is the time of the slowest component. And notice that we've isolated the slowest component. In other words, within a pipeline stage, there's no other component that comes either right before or after, right? So this kind of gave us a hint of how we want to go about forming our pipeline stages. So what's our throughput? Well, our throughput is 1 over the clock period. So basically, every 8 nanoseconds, a new output is going to be produced over here, right? So even though I'm taking multiple pipeline stages to compute a given output, as I start to fill up my pipeline, I'm going to be getting outputs every 8 nanoseconds, okay? And finally, what's the latency for a single input? Well, when an input starts over here, it has to go through 3 of these pipeline stages. So I have 3 times this 8, or 24 nanoseconds, is the latency for this circuit. Any questions about this? Great. So the strategy, as I just mentioned, is to basically identify what's your slowest component and put pipeline registers just before and after that component. And then the rest of them will sort of fall out by having to cross these wires in the correct direction and always going from this one terminal to the other, and these two terminals are connecting all of our outputs. So in this particular circuit, we have just a single output. If you had multiple outputs, then this first contour here would have gone through every single one of those outputs. All right, so let's continue further analyzing, when is it useful to add a pipeline stage and when is it not? So we're going to take a look at this simple example over here. I've got a combinational circuit with modules A, B, and C, and the delays of A is 2, and of B and C is just 1 time unit, okay? So what's the combinational delay of this circuit? What's the longest path? 4 nanoseconds, right? And so basically a 0 pipe is equivalent to a combinational circuit, means we haven't put any pipeline stages in. And the latency of that is 4. And basically, after every 4 time units, we would have completed processing a particular input, and it would be okay at that point for our inputs to change so we can begin a new computation. All right, well now suppose that I make this a 1-stage pipeline. What's that going to look like? Where is my register going to be if I have just a 1-stage pipeline? Well, we said we always have to have registers on our outputs, right? And so this is a 1-stage pipeline. So what is the latency of this circuit? It's still 4, right? Because I have to go through A, B, and C within one cycle. And the throughput of this is going to be 1/4. Now it's a little bit more explicit because we actually have registers that hold your values and make sure that they don't get corrupted while the next set of inputs is being evaluated. All right, so now suppose that I want to add another contour here. And let's say that I draw this contour here. So now what happens? Has my clock period changed by adding the second pipeline stage? It has, because now within every pipeline stage, my longest path is just 2 time units, right? So either I have to cover A, which is 2 time units, or I have B in series with C, which is 2 time units, okay? And so what does this mean? This means that my T clock is now going to be 2, but now I have 2 stages, and so my latency is going to be 2 times that T clock, and so I still get a latency of 4. Everyone see that? But my throughput has now improved, because every 2 time units, I'm going to get a new output coming out of this 2-stage pipeline circuit. So this is clearly going to have better performance than the first 2, okay? Now, what happens if I add, yet a third contour? Is it always going to give me a better circuit to add more and more pipeline stages? What do we think? No, right? If we look at this example, let's see what happens. Here, where I have a 3-stage pipeline, my slowest component continues to be 2. So my clock period has to allow for A to be able to run in 1 clock cycle. And so my clock has to still be 2. And now I have 3 stages, each of which is too long. And so I have 6 time units. It becomes my latency of the 3-stage pipeline. So I've actually made my latency worse by adding this 3rd pipeline stage, okay? And my throughput continues to be, 1/2 because I'm still getting something out every 2 time units, but basically you would never want to do this because there's no reason to, number one, add more hardware, which is, the registers that you've added in this extra path, and more importantly, make your latency worse without benefiting on throughput. Okay, the last thing I wanted to mention here is that as you draw these contours, you may end up in situations where you have more than one register along the same wire, between, two different modules. That's perfectly legal, and sometimes you have to end up with that in order to end up with a valid pipeline. So just be aware that, that you might see things like that, and you do in fact want to account for the multiple registers on the same path in order to ensure that your inputs are continuing to be processed. In other words, X sub I should always go with Y sub I, and so on. Okay, so one last thing with regards to pipeline components is that another way of improving the performance of pipeline systems is suppose that, I take this module A, which had a latency of 2, and in itself, I couldn't, as it was, I couldn't make my clock period be any better than 2. But suppose that someone was able to give me a pipelined implementation of A, which now has two pipeline stages in it, and each of those stages takes 1 nanosecond, okay? So my A still behaves as before, in that its full delay from input to output is 2 nanoseconds. But what changed by adding this pipeline version of A instead of my original version of A? What can I set my T clock to in this new circuit? I could set it to 1, right? So basically, I could pipeline this circuit as follows. I have 1 contour on my output, 1 contour that separates out C, and then 2 more contours that go through these registers in this pipeline version of A. So remember, if you have these pipeline subcomponents, you need to ensure that you have a contour going through each one of those registers, okay? So in order to fully execute what A needs to do, you must allow for 2 pipeline stages just for A, okay? And so basically what I end up here with is a 4-stage pipeline, but now my latency continues to be 4 because I have a clock period of 1, and my throughput has improved. Now I'm getting an output out of the circuit every 1 nanosecond, or 1 time unit. Does everybody see that? All right, fantastic. Okay, so let's do one last example before we move on to the next topic for today, which is, suppose that I give you this circuit, and I ask you to pipeline it for maximum throughput, and at the same time, you want to try to minimize the total latency. So let me just quickly draw this on the board. So we have a 2-component, 3-component, 4-component, another 2, and another 1. So who can help me figure out how to pipeline this? So what's the first thing I need to do? What did our little recipe tell us we have to do? Where's my first contour? Yeah?
Separate the inputs and outputs.
Separate the inputs and outputs, and I do that by basically making a contour on my output. Okay, so I make my first contour that crosses all my outputs. In this case, I have just a single output. And so here are my inputs side, and this is my outputs. Right? So my arrow is crossing from input to output. Okay? So I've started. Now, what do I need to do next? What's my slowest component in this circuit? The 4, right? So I want to try to isolate that 4. So how could I do that? Well, let's say I add, 1 contour that comes over here on one side of the 4, and then I do another contour that comes over here on the other side of the 4. Okay? So now I've isolated this 4 into its own pipeline stage. Am I done? No. What is still missing here? I still have a sequential path that's currently in the same pipeline stage of 2 plus 3, right? So that would make my T clock have to be 5. So in order to make my T clock 4, which is the minimum that I can make it, I need to add yet another contour that goes through 2 and 3, okay? So now let's take a look at what I have here. I have 1 stage, 2, 3, 4 stage pipeline. My T clock is equal to 4, right? And so let me draw these out for you here on the slides. And so what's the latency of this circuit? 4 pipeline stages, T clock equals 4. So 16, right? And my throughput is 1 over 4. Every 4 time units, I'm going to get a new output out of this circuit. Is everybody comfortable with what we did there? All right, in recitation, you're going to do a lot more of these examples. Okay, so now for the rest of today's lecture, we're going to move on to seeing a little bit about, we're going to focus on a particular problem, which is how do we build multipliers. And while we do that, we're going to consider alternative strategies of building that multiplier. So we're going to consider, a combinational implementation, we're going to consider a pipeline implementation, and again, another variation of that. And so the idea here is to really give you a sense for how your performance can change depending on how you go about implementing these more complex circuits. Okay? So let's start out by first just going through a binary multiplication example to make sure that we all understand how to do binary multiplication. So what do we have here? We have a number 1101, which corresponds to 13 in decimal, and we want to multiply that by 11, which is 1011. So how do I go about doing this? Well, it's just like decimal multiplication, where what I'm going to do is, depending on whether this bit is, each one of these bits is 1 or 0, I'm either going to add this 1101, or I'm going to add a 0 to my partial sum. So here's another way of expressing that. So I have basically these values here called m sub I, which is what I'm adding to my partial sum. And the way that I determine what each one of those is depending on the bit of A that I'm currently looking at. If that bit is 0, then I just put a 0 in. If that bit is 1, then I put B in. So let's take a look a little bit more closely. So what do I mean here? So let's take a look at what's happening in the first addition. So my least significant bit of A is a 1. And so that means that I want to go ahead and add the value of B, which is 1101. Okay? And so that's what I do here, and I end up with 1101 with a 5th bit added, so I have a carry of 0. Okay? Now, what happens is I'm going to look at my next M1, and that's going to correspond to bit 1 of A. So bit 1 of A is also a 1. And so again, I'm going to add 1101, except that this time I've shifted everything over by 1 bit. Okay? My 3rd bit of A is a 0, so there I'm just adding a 0. And finally, my 4th bit of A is a 1, and so I'm adding again 1101, each time noticing that I'm shifting by 1 position. So a couple things to notice here. The first is, in addition to the shifting by 1 position, this one's kind of a little bit trivial, but basically this first addition was kind of unnecessary because you always start with 0, and so you're just going to end up with the value of n0, so there's no need for that extra adder. The second thing that I want to point out here is that this example is using unsigned binary numbers, okay? So this wouldn't exactly work for signed binary numbers, and in lab, you're actually going to get to play with that and see how you need to multiply the circuit in order to handle signed two's complement numbers in these multiplier circuits. Okay, so now that we understand what the algorithm looks like, let's go ahead and try to build a circuit that's going to do this multiplication for us. So we're going to start out as follows. So we've mentioned that, we have these m sub i's. And so let's draw these in. And for starters, you can think of these like a multiplexer, although there are easier and better implementations than a multiplexer. But basically, what is this equation saying? It's saying that my select signal is my a sub I. So in the first one, it's A0, then A1, and so on. And depending on the value of A sub I, either I'm passing a bunch of zeros, or I'm passing the entire value of B, all the bits of B, okay? And so that's what these four boxes represent. Then I have, 4 adders here. And so we'll add these 4 adders to our circuit. And what is it that I'm adding in these circuits? Well, for the first adder, my second input is just a bunch of zeros, okay? Now, I perform this addition, and what happens? I get a 5-bit output. Notice that at this point, the least significant bit is actually already the final output of my full multiplication. But for the other bits, I still have more work to do. And so this is where the shifting comes into play. Okay, so now my next m sub I is working on these 5 bits beginning with bit 1. So I basically take bits 1 to 4 as my next input to my next adder. So now I add those again, and now I have a second bit that's now ready it's actually the return value. And again, I continue in the same manner until finally I end up with a 8-bit output, which corresponds to the multiplication of these 2 numbers. Any questions about this circuit? Good. Okay, so now let's go ahead and try to analyze, how is the circuit going to perform? So, in order to do that, I want to first have you, rethink a little bit what it is that we're doing here. And so here I've redrawn this multiplication just like you would do decimal multiplication, where in each row I've taken, first bit A0 and it's multiplied times B0, B1, B2, B3. Then I shift over by 1, I do the same thing with A1, and so on, okay? And so I've got a bunch of these intermediate, we call partial products, which I need to produce. So what circuitry, can I use in order to produce them? Well, if I take a look at what these are basically each of my m sub i's. So in the previous slide, we saw that we could implement it as a multiplexer. But it turns out that you can actually use much more simple circuitry than a multiplexer. Because remember, multiplexers are very expensive, right? If I have a 32-bit multiplexer, it consists of, if I have to think about it as how many 2-input multiplexers that consists of, there's at least, log n of them, basically a tree of multiplexers to produce this 32-bit multiplexer. So it would be nice if we could do something much more simple. So if we take a look here at this binary multiplication table, what do we see? Well, we see that if the top corresponds to A and the rows rows correspond to B, well, as long as A is 0, then it doesn't matter what B is, our output's going to be 0. And if A is 1, then the only time we're going to get a 1 on our output is when B is 1. So basically, I have to have both A and B be 1 in order to get a 1 in my output. So what gate does that look like? An AND gate, okay? And so I can produce all of these tiny little partial products by just using a very bunch of AND gates that are going to produce each of these partial products. And this is telling you what's the expected length of my output. So if, in this case, we treated both inputs as being the same length, but if you have a n-bit number and an m-bit number, the expected output would be n plus m digits. And so the easy part is going to be these AND gates. The harder part is going to be, well, how do I go about adding all of these, intermediate products? So here's, another way of looking at this combinational multiplier. It's basically the same circuit that I just showed you, but here I'm actually pointing out every single one of the full adders and what inputs and outputs it's operating on. And in addition, we've replaced the boxes of the m sub i's with these simple AND gates, okay? So if you look at the top row, I don't even have to do any addition. It's just a sub 0 ANDed with b0, b1, b2, and b3. Okay? Then what are the rest of these? Well, full adder, you guys are familiar with. And so I'll just remind you what the definition of a full adder is, which is it has three inputs, A, B, and a carry in. And the sum is going to be the exclusive OR of those three inputs. And the carry out is going to say that if at least two of them are equal to 1, then I'm going to get a carry out, okay? Now I have this additional module here labeled as HA. This is a half adder. What this means is that it's basically a simplified full adder. How is it simplified? It's simplified because instead of having 3 inputs, it only has 2 inputs, okay? And so some of this additional logic basically goes away. And so the equations for a half adder are that the sum is just the exclusive OR of A and B. And the carryout, you get a carryout if both A and B are 1. Okay? So this circuit is basically the same thing as we saw before, but now it has all these full adders explicitly shown here. And notice that that each of these adders is shifted by 1 to deal with that shifting that we saw in the previous slide. All right, so now let's try to analyze the performance of this thing. So, if each of my A and B are n bits wide, how long is it going to take me to produce the output of my multiplier here? Is it going to be order n squared? What do we think? Well, it turns out that it's much less than order n squared, which is a good thing. And it's actually order n. So let's first try to understand why that's the case. So let's see what happens. Well, in this circuit, what's happening is that it does take order n to go to do a single addition, or basically one row of this circuit. However, notice that because of the overlapping of the columns, this addition can start as soon as this one's done. So I don't have to wait for the entire first row to be completed before this set of adders begins to work, okay? And so if I think about what my propagation delay of this is, it's basically proportional to the number of bits of B, which is n, and then I basically have 2 more full adders that I have to go for every additional row, okay? And so given that I'm only adding another constant for every row here, I'm ending up with something that's of order approximately 3n, but it's still not n squared, okay? And so what's my throughput of a circuit that has a latency of order n? Well, my throughput is 1 over n, right? It takes time proportional to n to produce one output, and so that means that every n time units I can produce a new output. And what about the area of this circuit? How does it relate to n? Is that going to be linear in relation to n? No. It's going to be quadratic, right? Because I basically have essentially n times n of these full adders, okay? So this is, our combinational implementation of this multiplier. Now let's think about pipelining this multiplier and see how we can improve performance by doing that, all right? So here's our first attempt at pipelining this. So what do? I draw a contour that goes through all my outputs, right? And now I draw, let's say, another contour that connects those two endpoints. And then I draw another contour, and so on, okay? So what do we think of this pipeline circuit? Is it a valid pipeline circuit? It is, because if I go from every input to output, I always have, these, right now, 3 registers or 3 contours that I'm crossing. Okay, so it's a valid pipeline, but what's the clock period at which I can clock this pipeline? In terms of the clock period of a single full adder. So if I could clock a full adder takes 1 nanosecond, could I set my clock to 1 nanosecond for this circuit? No. Why not? Because within a single pipeline stage, I have multiple of these full adders that have to be executed sequentially, right? So really, my clock period here is proportional to n, right? And so even though I've created a valid pipeline, what does this thing look like? Well, my clock period is of order n, and so that means that if I have, n stages corresponding to the number of rows here, then my latency is going to be of order of n squared, right? Not such a good pipeline. And what's my throughput going to be? My throughput is going to be 1 over n, because it's 1 over the clock period for this circuit. Okay? So let's see if we can do better. Well, what we want to do, basically, is break this long chain when we draw our contours. So we're going to try again. We're going to start out with a contour that goes through all of our outputs, but now we're going to draw our contours a little differently so that we try to have at most 1 full adder between every pair of registers. So what would that look like? So I start here and I draw, this additional contour that isolates this last full adder. All right, now I do another contour, isolates this full adder. But on the next step, I notice that I can actually put these 2 full adders at the same time because they're independent of each other, okay? So they can be in the same pipeline stage. And so I continue basically drawing diagonal contours through this circuit as follows, okay? So now, let's analyze the performance of this circuit. What's my clock period now in relationship to n? If my full adder is 1 time unit, can I clock this at 1 nanosecond, or is it somehow proportional to n? Well, what has to happen here in a single pipeline stage? I only have to go through 1 full adder. Okay? And so that means that my clock period just has to allow enough time for a single full adder. It's not a function of n. Okay? And so that means that our clock is a constant or order 1. Okay? Now, what about my number of stages? Well, the number of stages is, you could count it as, n in this direction and n in this direction and a couple more. But basically it's of order n. And so what's my latency going to be? My latency is going to be the clock period times the number of stages, which is also order n. Okay, so much better than my combinational multiplier. And my throughput is going to be order 1. Basically, every time unit, I'm going to get some new output coming out of this pipelined multiplier. Okay, so things are looking pretty good. Now, of course, this is a pretty complex circuit, and so you might want to consider yet another alternative, which is what we call a folded multiplier. So a folded multiplier is basically trading off area for performance. And so what does that mean? If I go back to this picture over here, I could essentially, instead of having a bunch of these 4-bit adders, I could use just one of them and put a register between them and reuse that same adder over and over and over again over multiple cycles. Okay? So a way to think of that is basically with a circuit like this. So what happens here? I've got my A and my B. I'm looking at one bit of A for every given iteration. And this is just my set of AND gates, which AND that bit of A with all my bits of B. And then I'm adding my partial product to the result of that AND gate, okay? And what happens is that I only have a single n-bit adder here. And so I can't perform all of these additions in parallel. Instead, I have to do, the addition of one row of my multiplier, and then in the next cycle, another row, and I keep saving my intermediate values in these registers, okay? So let's just quickly analyze the performance of this. And so now here we have 2 cases to consider. How I go ahead and implement this adder is going to affect the behavior of this folded multiplier. So if my adder is a ripple carry adder, then essentially the T clock at which I can run this sequential circuit is still of order n. And so that means that I have not only a T clock of order n, but in addition, remember that I'm executing this little pseudocode m times, which corresponds to the number of bits of A, so that I can actually do all of the additions associated with each of my bits of A. Okay? And so the result is that I have a really terrible latency of order n squared, and also a bad throughput. On the other hand, I can also have the same model of my circuit, but instead of having, a ripple carry adder, I could basically have, let me just quickly go back here, an adder that corresponds to one pipeline stage here, okay? So if I had an adder that looked like that, and then just folded it over, so that I used it over and over again, then how long would it take me to compute this multiplication? Well, I have time proportional to n to go through the number of stages. And so basically here, my T clock is proportional to 1, because now I've changed the way in which I'm folding this multiplier. But my number of stages is still n, but so now my latency is much better. It's of order n, not n squared. Okay, so basically what we want you to see here, and you're going to do a lot of this in Lab 5, is to realize that depending on how you put these circuits together, you're going to get different performance. And so depending on whether you're trying to optimize for area or latency or throughput, you might want to pick a different one of these designs. All right, thank you very much. We'll see you guys tonight at the quiz.